Good afternoon. Good afternoon.
Good afternoon, sir. Good afternoon.
Yeah. Can I test whether my slides go up or no?
Yeah, just a second, just a second. कहाँ थे, sir? Can you please stop sharing? Yes, yes.
Okay, now sir, you can share your screen.
Over to you, Dr. Jha, sir.
Just a sec. Just a sec. Yes, I'm trying.
Yes, sir. You have shared your screen. We are seeing your screen.
Is it there?
Yes, sir.
Yes,
Introduction
sir.
to mechanics.
Yes, sir.
Introduction to quantum mechanics for quantum computing and some aspects.
Yeah.
Raman Kumar Jha. Yes, sir.
Then I'll just clip it out also so that you can see whether it is moving.
Yes, sir. It is moving, sir. Yes, sir.
Good now. Good now. Thank you so much.
Yes, sir.
Welcome, sir. Welcome.
Shall we wait for 2-3 minutes, sir? Because
Yeah,
Yeah.
we scheduled at 2:30. Now it is
uh,
2:25. So we'll wait for 3-4 minutes. Let the participants join.
Actually, they must have been bored already so many times, possibly a lot of repetitions also. So,
Sir, is it possible to view in a full screen, in full mode?
yes.
Yes.
yes, sir. Yes, sir.
Yes, sir. Thank you.
Perfectly all right, sir.
Fine. All right.
Yeah, fine, fine.
So these faculties are, as I heard somewhere, they are from engineering background. But
Yes,
Yes, sir. All are engineering background. Mostly are engineering background.
and they are also working in the area of quantum computing.
May not so, not all,
not
but
necessarily.
maybe few staff will be working on the research.
Okay. So
Yes, sir.
it's a type of an exposure to them about a new field.
Yes, 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 yes. Just 2 minutes and we will start.
Yeah, I'm ready. No issues.
So I request Dr. S.V. Gumathe sir to introduce Dr. Raman Kumar Jha sir.
Yes, sir. Thank you. Good afternoon, all. I, Dr. S.C. Gumaste, Professor and Head, Department of Information Technology, Amity's Institute of Technology, Nashik, welcomes you all for 9th session of FDP on quantum computing. It's my privilege to introduce a renowned and eminent personality, Professor Dr. Raman Kumar Jha. Basically, sir was a Chinese school student during his primary and secondary education. This itself reflects about dedication, devotion, and systematic life pattern of Dr. Jha, sir. Sir did basically BSc, MSc, PhD Physics from University of Delhi and later MTech in Information Technology from SMIT Sikkim. Sir worked with various positions including assistant professor, professor, head of IT department, principal, dean, and currently as vice chancellor of Amity University, Jharkhand, Ranchi. Sir now leads an institution and is responsible for monitoring and promoting the efficiency and good order of universities. As already said, Sir is known for his discipline, dedication, and divine approach. He is also responsible for providing strategic direction to the institution's employees and for fostering the university's high-level contacts. This includes direct personal engagement at the highest level with ministers, policymakers, and industry leaders to champion the interest of both university and work and role the higher education sectors as a whole. Dr. Raman Kumar Jha, Jha's Vice Chancellor's office also organizes several student meets designed to provide an opportunity for him to meet informally with representatives of the student community for the mutual exchange of information, ideas, and opinions, as well as opportunity for students to speak directly with a Vice Chancellor on matter of concern to them. His deep sense of spirituality and human values makes his task people-oriented and he is passionate about it. His scientific interest focus on information technology, theoretical and experimental high energy physics, namely quantum computation and information systems, distributed computing, etc. With this busy schedule, Sir wrote several books and published a huge number of research papers. On behalf of Amity's Institute of Engineering, I welcome you, sir, and we are all eager to know more from you on quantum computing. Over to Dr. Jha, sir.
Thank you so much for the nice introduction. I firstly will begin by thanking the Amity Bhujbal Knowledge City College and especially Professor Vijay More sir, who has given me this opportunity to speak to the faculty members. And these are, I suppose, the faculty members who are interested in pursuing something or the other, maybe in quantum computing area. So I have also tried to attend some of the earlier lectures and understood that there are many people who are involved in India and abroad exploring this particular field, which is new as well as established. I'm saying this very categorically. Quantum mechanics is established, but quantum computing is new. So here is a possibility of a marriage which can take place between the concepts of quantum mechanics and the device made up of it for computing. Now, therefore, I would try and only possibly introduce the topic in the manner I can, in the best manner I can. And I would be happy to interact at the end if time permits. Some aspects which I'll keep adding and skipping my slides as well. Please forgive me that. In case you need the slides, I'll send it later. So this will be a session only to make you understand where are we limited, what are the strengths, and how possibly can we explore or exploit the quantum mechanical concepts for real world applications by using it in the computational industry, I would say. So that's where we begin with, and that is the topic given to me, quantum mechanics for quantum computing and some aspects. I hope I was seeing the most of the talks were on quantum computing rather than quantum mechanics. So I have focused more on quantum mechanics and its understanding. Please bear with me. In case of questions, I can take it up. So if you talk of quantum mechanics, we cannot but understand that this also was not there with us for long, has not been here for long. It is almost 100 years old system that we have, which we call as quantum mechanics. Earlier than that, for almost 300, 400 years, we were dealing with something which is called classical mechanics. Now, for a layman, a classical mechanics system is one where the masses that which we are dealing with are large enough, like the sun, the moon, the earth, the planets, even including the mountains or things which are voluminous as well as massive. So if the mass is large and the velocity with which they are moving is small, or also not that small, but then comparatively small with the thing, but it comes under the realm of classical mechanics. But then as we moved on to the smaller and smaller particles, when the masses became smaller and the velocities became large, please understand the difference. So when the mass becomes smaller, that means say an atom, and then we get into the atom and then try and understand the movements or the characteristics of protons, electrons and neutrons inside the atom. So those are atomic level measurements or involvements and understanding. So the masses were very small. Say that of an electron, it is too small a mass. And then if we think, see those electrons or protons, we could see that even those can be subdivided. So there were subatomic particles as well. And that gave rise to the quarks, the leptons, and their interactions at a level where the classical mechanics drastically failed. So the Newtonian mechanics, which we call as classical mechanics, had its inadequacies at the atomic and subatomic levels. What were those? Some of them I have listed here. Remarkable stability of Rutherford's atom. What is this? When we see the atom as given by the model by Rutherford, Bohr, and etc., it was seen that the nucleus occupies a very small space, and then the electrons are revolving around these nuclei, and it is also seen sometimes the nuclei, the electrons fall from one orbit to the other. Now, if it is revolving with some amount of charges that they carry, it is obvious that classically we think that the energy will go away. Since it is revolving slowly, it should fall to the nucleus, and therefore atom should lose its significance. But that was not happening. The atoms were remarkably stable. So every atom is seen as stable. That means electrons which are revolving around the nuclei have got a fixed orbit, or maybe it jumps from one to the orbit, the other, depending on the energy that it gets. So that's the first point. And at that point, the classical mechanics seem to fail. Then atomic radiations. It was also observed that the radiations at these levels, when the electrons fall from higher level to the lower level, we had radiations coming out. and it was seen that the frequency was inversely proportional, or it was proportional to 1 by n square. So as it went from one level to the other, or nth level to mth level, so the frequency dependent radiations were given. So that means not all possible radiations were allowed, or you can say that energy could not take all the values. It was dependent on the orbit level that it was in, and it was also dependent on where it was going, which means it was dependent on the energy difference between the two levels. It is understood by now by many. Similar things were also seen, that black body radiations, it was observed that the radiations were proportional to the frequency, and it was quantized. So this word quanta came from the fixed, or maybe I would say proportional to frequency type of a connotation for energy. So energy values were not continuous but quantized. That is how it came. And then ultimately the photoelectric effect proved the quantum impact of the light. The light was, when the photoelectric effect was essentially that when light fell onto a metal, it was able to knock off the electron if the energy of the photon was higher than the binding energy of the electrons. So simple. So the photons were able to knock off electrons, and therefore it gave rise to electricity. So this was called photoelectric effect, and obviously it was given by or experimented by Einstein, and he got the Nobel Prize on that. So these were not again possibly explained by classical realm. Failure to measure the things at the atomic scale happened. So if we had to measure the position of an electron at any point of time, it was not possible by using the classical systems. So we had to think of quantum systems automatically, or maybe we had to evolve to a system in a way that we are able to explain the physical phenomenon in a more mathematical or clarified form and with precision. So what were the problems in classical mechanics has been listed, some of them, there are many. And then what was the new thing coming in? And I put it in 3 words here: discreteness. So that was included in the quantum concepts. Then duality was a new term which came, and it was observed that the photons or the light particles not only behaved as particles but also simultaneously behaved as a wave. So it means that it was a particle as well as a wave. This concept of duality, when it came, it hit the world, and then slowly it evolved to a level that every particle will have a corresponding wave. That means every particle will also have a lambda corresponding to it, a frequency corresponding to it, no matter how small or big. So that was a new concept. And because of the duality in nature, it was then seen that we were, because of this duality, not able to really measure the position or sometime other parameters, which will come to slowly, to the extent of accuracy that we needed. So that means there was an uncertainty inbuilt in the physical world rather than the measurement technique. So that's where these 3 words bring us to the quantum world. Historically, if you see, we began almost at 1901, so it is almost 100-year-old quantum mechanics that we have. With in 1920s, we had the concept of Heisenberg's uncertainty principle, and Schrödinger and Dirac came on to make a new mechanics, new dynamics, new system of dealing with these quantum particles, or maybe we call them as smaller particles, atomic scale particle. In 50s and 60s, so just 30 to 40 years, we have developed considerably well, and both in theory as well as experiments, and a lot of things were predicted in quantum mechanics. And there were developments of the quantum mechanics itself to field theory, and relativity came in, then relativistic field theory, and then ultimate to string theory, and so on. We are not going there. So our aspect is that quantum mechanics itself developed considerably, and it also did experiments based on quantum adiabatic processes. Without going into detail, I'm just putting in the words. Generalized quantum statistics, and wherein Indians contributed a great deal. The methods of stochastic quantization. So it was all about quantization and discreteness of energy existing all around us. Then the role of the symmetry itself in the non-relativistic quantum mechanics. This happened almost in the independent era that we were in. And then as it saturated, we started thinking in terms of going deeper into the atom. And more deep we went, more uncertain it was, or more, I would say, energy was required to get into that place. If you have high energy coming in, then only you can probe smaller and smaller distances. So the whole physics world was trying to establish accelerators where high energy could be produced. They were accelerated in the accelerators, and then it was bombarded on the target. And the probing of each individual atom or the molecule was done to understand what is happening inside. So that's the physics area. Coming to the quantum computing aspect, which is where I have to link the two, that application to quantum computing about the quantum concepts came almost like 1980s, when Feynman himself, he was a physicist, he said that some quantum effects cannot be simulated on a computer. And that time, whatever computer we had was nothing but a classical computer. So that they thought of using quantum effects. So can we have quantum effect or quantum properties being utilized to make this computing? What was that he wanted? He wanted to simulate the time evolution of a system. See, this has been the hunch for physicists, that if you have a system and you understand the system well and its constituents and forces all inside it, then you leave it to time and let us see how it evolves. It has been very well understood that a system whose initial conditions are disturbed even by a small amount may evolve into a chaotic system, or a very systematic evolved system where everything is very well understood and seen and can be measured. So this simulation was in the mind of Feynman, that he wanted to see the evolution of a system with time. He could not do it using that quantum, the classical system at that point of time. And therefore, he just hinted that classical computers have limited scope and some effects cannot be studied there. Then, and that gave rise to a lot of researches in this area, and you must have heard many other talks already. In 80s to 92, almost Deutsch and Josha gave a concept of a quantum parallelism. I'll try and explain this word in a better manner, because there lies the power of quantum computing. Quantum parallelism is essentially to explain the exponential increase in the number of states which are provided by the quantum states. If you just look at the classical system, zeros and ones have been doing the wonders already. But if you have infinite combinations of zeros and ones only, then naturally the data storage becomes large. This is simple. But then manipulating that data parallelly in number of states, because that is infinite states. So some part can be done here, some part can be done somewhere else, some part can be done at some place, and then all these modules can be combined to give you the result that you are expecting. So this is called quantum parallelism. The quantum power, the power of the number of possible states which have been generated because of quantum mechanical principles, and one of which is superposition principle here, makes the power so huge. And the moment it is done at n number of places and it is done simultaneously, naturally the speed of calculation increases, the time reduces, and you can also deal with large number of such data points. So that's the power that we had. and these few years, 20 years, has seen that parallelism coming up in a big way. Then we had some issues that there are problems which we may not be able to solve using quantum mechanics also, but then there came some techniques or algorithm by Peter Shor, which solved the integers into prime numbers in a polynomial time, otherwise not possible in this, and this led to a great surge of the activities in that area. Coming back, what are the barriers that quantum system have? There are only two barriers. One is the concept itself, and the second is notation. Now, notation is something that is a matter of practice. We can practice and we can understand. I have done quantum mechanics and also did PhD in the particle physics area, and therefore I have spent my life almost 25 years now dealing with these systems. So what are the concepts? I'll spend a few minutes here. Quantum state space. What is this? If I see a particle or a mass in a classical system, I would weigh that and say that this is the mass, this is the charge, this is the velocity, this is the momentum, all that. So these are characteristics of a particular particle. Similarly, in a quantum space, we say that this is the state of a particle or a state of a system, because there is nothing now particle or wave, it is all the same. So entity, you can say that, or any quantity, any quantum mechanical entity will be explained in terms of certain things, and the whole set of all those characteristics or quantum numbers or measurements, whatever you call, those together define the state of that system, and that is called the quantum state. And this number has increased starkingly, and I would say exponentially, and that is the good news. Second concept, so that is the first concept about the state itself and the space, which is infinite dimensional. Second is the measurement. It is said and that if a man is put in a dark room, completely dark, no light coming in, and he is given a stick in his hand, and there is a ball in some corner in the room, and he is asked to locate the ball. Now, if he starts locating the ball in that dark room, don't we think that moment he would touch the ball will move? That means the position cannot be determined accurately. So the moment he touches that, or the moment the measurement is done, the state changes. Now, this is a very, very good concept which is to be utilized in quantum cryptography. If you are sending something which is very secret, and moment somebody touches it, it changes. That means you can know that somebody has tried to touch it. So the concept of secrecy or security is highly enlarged. So nobody can touch it is another thing. So but then you can understand that somebody tried to touch it. So the measurement makes the system collapse to a particular state. There are combination of states where the space is how the space is explained, but the moment you do a measurement, it decoheres into a particular state. Very important concept of quantum mechanics. And then entanglement, it is something like this: the butterfly flaps its wings in New Zealand and the weather changes in India. Something like this, which means there is some measurement done somewhere else, and particles are entangled or correlated or related in a manner that a measurement done there definitely gives us the measurement of this place as well. This is called entanglement. And if that happens, we are using this concept of quantum mechanics to understand that if I understand this part of it, I understand the other one as well, because those are entangled. So this concept is being utilized to a great extent, but this is also a barrier because many people do not understand it. Quantum mechanics is totally understood as far as these are concerned, and the matter therefore is only to be converted into practice or making a quantum computer using these. Next is notation, which is the Kett and Bra notation, which is matter of practice, as I said earlier, and any quantum mechanics books will always let you understand this. Coming to the quantum systems, once again, some things which I have put to make you understand. The computational space increases exponentially, I just said this. Second is this exponential parallelism leading to faster algorithm concept of a state comes in. I hope you are understanding if you're listening to me carefully, because if you miss one, you'll have to miss the other one as well. Because there is an exponential parallelism, parallelly so many places computations can happen, it will obviously lead to faster algorithm concept. Then the principle of superposition, that if there are n number of possible states, then a particle can exist anywhere at any point of time. So there is a probability of existence of the particle at any point of time. Therefore, the net state is nothing but the superposition of all those particles, the waves or the states. Measurement proves tricky. This is what I said. Tricky because of that dark room concept. You can correlate that. It is tricky, and thus it requires non-traditional programming techniques. Very important. And therefore, this quantum systems become difficult because traditional programming techniques are not working here. So we will come to the algorithms, some of them which have been made, and the entanglement itself is a part and parcel of the system. Now, what are these non-traditional techniques exploiting the power of quantum parallelism? If you have heard of the various lectures, again, everybody must have used these two algorithms, Shor's algorithm and Grover's algorithm. The two are using two different concepts of quantum mechanics. The Shor's factorization method manipulates the quantum states so that the common property of all the output values like symmetry or periodicity is read off or utilized. Say, if I understand that the moon goes around the sun, around the earth in this manner, and then it repeats, I have to understand only one cycle. So this is a common property. Once I understand the common property or periodicity, then I have understood the problem. And physics is known for breaking the problem into smaller and smaller parts so that each part you understand and then integrate. In fact, that is how Britishers ruled us. They divided us into smaller parts and then ruled us. So quantum mechanics has this inbuilt property, or physics people have intelligently used this, that they divide the problem into smaller parts, find the periodicity or maybe some type of a regular pattern, and then repeat the same. And that factorization is then done, which is much faster than this, the other algorithms existing. Second was the amplification technique. This transformed the quantum state to increase the likelihood that the output of interest will be read off. I have some interest. I want to know whether say somewhere this is the temperature, or temperature lies between this or that. So if I have to scan the whole system and take out the temperature, if I am only bothered about the small portion of Earth where temperature is to be read, then I must have the system itself or the state itself modified in a manner only that part is picked up. And that's the information technology all about. You pick up the information that is of interest to you. And if you have quantum also attached to it, nothing like it. It is like getting the best thing in the best manner, in the fastest manner. So that is how the two have, therefore two are using two different concepts of quantum mechanics, and they did it. Quantum systems have been successful, no doubt, and even in the computing aspects like quantum cryptography, you must have again got the hint of it. Quantum key distribution. So there are passwords or keys, you can see, these are distributed and this cannot be broken because of the large amount of data that you have, exponential data sets one has to scan if he has to find the solution. Then quantum teleportation, quantum dense coding. Now this dense coding is a new concept. Maybe you have been talked about it. Like you have to map the quantum bits with the classical bits, and can you have one quantum bit carrying number of classical bits together, or one classical bit having more number of quantum bits? That's the dense coding that you're talking about. That solves a lot of other problems of redundancy, etc. But nevertheless, all said and done, quantum mechanical systems are not deterministic. So if they are not deterministic, that means the results that you will get will always have some error. And that is where most of the scientists were worried that, well, no matter what, but quantum mechanical calculations will never give us the right results. No, the algorithm came, and we have now got concrete error corrections also done in the quantum mechanical system. Therefore, the results are reliable as we see today. So those are success stories that we have. But there are some questions which are still open. Whether the quantum computers can solve these NP-complete problems in polynomial time. See, everywhere computing essentially tries to reduce the time, and in polynomial time means the time which is within the reasonable limit of our calculations and measurements. It cannot be infinite time. Now, NP-complete problem, what are those? Maybe you have been told. I will tell you a little later as well. Whether useful quantum computers can be built or no. So these questions are open still, and therefore all the faculty members who are listening to me and have even little interest in doing it, if you're serious, you can attempt to work in these particular areas which are open questions, and this can give you Nobel prizes as well. How to build the quantum computers? Like the second question open was, can it be built or no? So I'm just giving you some techniques which are possible. There are more detail later as well. One is the using ion trap method. So ion trap method is one where electric field is there and there are some ions and they are manipulated and you make gates out of it. And the only problem they have is they need extreme vacuum states or situations, environment, and extremely low temperatures. But then that's one way of making quantum computer. Second is the nuclear magnetic resonance, NMR system, which we all know about it. Room temperatures, this will work in the room temperatures, and they use magnetic field. Third is the optical techniques. That means you are making all measurements using only light. So those are optical computers, optical quantum computers. And the fourth, which is the normal solid state techniques, which are actually used in classical as of now. Now, what are the requirements for understanding quantum mechanics? Linear algebra, classical computing concept must be there if you have to go to quantum computing. Then you must understand what is this Turing machine and all about it. I'm giving you this idea because these four things, if you master, you will be there as a player in quantum mechanical field or a quantum computing field. And then the complexity and its calculations in the computational field. Then if you're working and trying to make a model, the computer, then what models exist? There are just two models which have been thought of so far. One is the quantum circuit model and another is the adiabatic computer model. Adiabatic computer model is not something very different, but leading to the same results almost. Therefore, even if you study one, we are used to the quantum circuit model or any circuit model for that matter. Now, let me put in here only a concept. Even the classical computers that are in front of all of us now, do you think they are working on classical systems really? Or they are working on quantum systems? We have used the concept of diode there, triode there, transistors there, ICs there, very, very large scale integrated circuits have been made. These are all inside. They all are using quantum mechanical concepts. Tunneling, annealing, the concepts of the electron being beyond borders, transistors for that matter. These are all quantum mechanical concepts. So we are already using quantum devices, but we are calling our computers as classical. Why? That means the classical circuits which are using quantum mechanical devices are also still classical only. I hope you are getting my questions. If not, please ask questions. The present set of computers that we have in front of us are called classical computers, not because they are using classical devices, but because they are using zeros and ones binary system for all their storage of data and all the calculations or manipulations. That is why those are called classical. Instead of changing the devices, we don't have to change much inside the computer, but we have to use the different bases. Instead of zeros and ones, we will start using the state called or wave function, which is a combination of superposition of zeros and ones, and that is the quantum state we are calling. If you're using those quantum states instead of zeros and ones like classical computers, you will have the powers that we are expecting to have. So what is a quantum computer then? It's the next generation computers, a computer that uses the quantum mechanical phenomenon. I hope you're getting it, to perform operations on data through devices such as superposition and entanglement. Good news is not much of quantum mechanics is required, just a superposition and entanglement, which is very well understood in quantum mechanics. Next is the classical, which we are already using. They use the voltages flowing through the circuits, and concept of gates are there. Similarly, parallelism has been drawn, and we are now thinking or we are already talking in terms of quantum gates and so on. Now come to a new thing which I thought would be interesting as well as thought-provoking. Let's understand a metaphor which is in the quantum field. Look at this figure. There are 6 people all around, and all of them are supposedly blind. They cannot see, and they are touching different parts of the elephant, which is huge in size. So there is a metaphor that the blind men and the quantum adding vision to the quantum world. How are they together adding vision to the quantum world? So it is said that quantum mechanics is like the elephant, and there are different blind men looking at some aspect of it, still not getting the full and full feel of the quantum mechanics. That's where we stand. So blind man and the elephant, it was given by, of course, John in 1800s. So somebody on the top, you can say, they said it is very much like a wall. The next man came and he says it is like the spear, looking at the teeth that it has. The third, it says it is more like a snake. The fourth, looking at the leg part, says it is like a tree. The next man, looking at the ears, says that it is more like a fan. And the next one at the tail says it is more like a rope. So these are all 3, 4, 5, 6 different interpretations. Can you think of this analogy, that blind men will only look at the small portion, and like that also our visions are also limited. We also look at one aspect of the whole and interpret in our manner. That is the analogy that we have, and at the end you can see, though each was partly in the right. Naturally, they were all interpreting the way they were looking at it or perceiving it, and all were in the wrong. None could have the full feel also. So that's where it is. Therefore, we are left with this analogy that whatever quantum theory is, there are different interpretations to it as well. So if I interpret in my manner, that's how I look at it, and if that gives me result, that is a successful interpretation. And there are other possible interpretations also. We'll give some example. So what is quantum mechanics? Quantum mechanics is a theory It's a current standard model for describing the behavior of matter and energy at the smallest scale, like photons, atoms, and all that. I'll be faster now because I've already spoken about it, all this. Like all theories, it consists of a mathematical formalism plus an interpretation. So there are two things: formalism, which is the formula, and the interpretation. However, quantum mechanics differs from other physical theories because while its formalism has been accepted, formula has been accepted and all used for 80 years now, its interpretation remains a matter of controversy still and debate. And that is why Feynman sometimes said, nobody understands quantum mechanics. So interpretations are open like the Hindu Dharma. Nobody understands what is Hindu. Everything is Hindu. So this also is Hindu, that also is Hindu. So it's quantum mechanical in nature. Like the mind itself, our mind is quantum mechanical in nature. There are so many thoughts, so many interpretations keep coming every second. And every thought is my thought. So nobody can say this is, but then that leads to sometimes controversy and debate. So like the many opinions of the sixth mind, there are many rival quantum mechanical interpretations also in the market. Today we'll consider some of them. So interpretation of formalism, what should be the role of an interpretation? It provides link between the mathematical formula and the elements of the physical world. So if you are able to relate, then relate and repeat also the same experiment every time, you are there. Neutralize all the paradoxes. So if you have made a formalism and interpreted it, does it take care of all the paradoxes about the problem that you are attempting? Provide the tool for visualization or for speculation or extension. This is the whole aim of studying physics. If you say this is the formula which is valid, or this is one theory which is valid, can all the results be brought out using this theory? Can you speculate and extend to other areas as well? I was fortunate to do one particular one such a result or a research wherein our results were possible to be extended in the realm of solar spectra. Then another was the quark-gluon spectra, and third was the superconductivity realm. So three different realms we worked on that theory. So hats off to my guide and the system that we worked with. We evolved with that theoretical model, and it has been really successful in three different realms. And that is the type of theory which is going to be successful. It should not have a sub-formalism again. You cannot have a formalism and its sub. Should not make its own testable predictions also. Not that this theory will only be working here or there. If the classical mechanics failed, we brought up quantum mechanics. The quantum mechanics also had its limitations. We brought in relativity concepts. When the quantum and the relativity concepts combined together, the physics grew, and we got the concept of a field theory. The field theory was an extension, and relativistic field theory came in. Then after that, another few things again, limitations were removed, and we had the string theory coming in. So that's how the theory progresses. If you have one theory for everything, that is the theory of the universe and the God. But every theory is falsifiable, that means challengeable, and that is science. It is found to be inconsistent with the formalism and experiment. It is always left to challenge. So interpretation, what is, let's have one example. For example, force is equal to ma is a formalism. Well, how do you interpret this? That the vector force of a body is proportional to the product of scalar mass, which is positive, and the second time derivative of its vector position, which is acceleration. That is the interpretation. But what is this interpretation doing? It relates the formalism to physical observable. What is the physical observable here? Force and the acceleration. It avoids the paradoxes that would arise if m is less than 0. So it says m is positive, scalar. And it ensures that this is applicable for all types of force and acceleration within a limit, of course, that is classical system. So there are still paradoxes which exist. I'll be fast enough here to make you just give you a feel of it. One paradox which existed was called the Einstein's bubble. The photon is emitted from an isotropic source. It is spherical wave function. You can see if you look at the screen, can you see my arrow? I don't know. If you can see, there is a wave function, and the quantum mechanical system is explained in terms of wave function. Just down below, diametrically below on the lower bubble, you have the psi. That means the light, the photon is emitted from a center of that. So the moment it is emitted, there is a wave function which is there inside, and that is expanding. All right. Then it reaches a detector. Now, if you go back, there are 3 detectors, A, B, and C, with the arrows in green. So if it reaches one of the detector A, then the psi bubble pops and disappears. Now look at this interpretation and the situation. The question is then, if a photon is detected at a detector A, how does the photon's wave function at the location of detector B and C know that it should vanish? Now this is an open question and a paradox. If a light source is there in the center, the bubble expands, but it goes at one place and then it is detected. The moment it is detected at one place, it is not there in B and C. Is it a paradox? Look at it. Now if it is like something like this, it is as if one throws a beer bottle into the Boston Harbor and it disappears, and its quantum ripple spread all over the Atlantic. What is happening? It is disappearing, and this ripple is going all out like this. Then in Copenhagen, the beer bottle suddenly jumps into the dock and the ripple disappears elsewhere. So once the measurement is detected, every other state will go away. That is what was called decoherence, or this was the measurement impact. The moment it is measured at one place, it collapses to one state, and therefore you can see the bottle once again. And that is what quantum mechanics says happens to the electron and photon when they move from place to place. So it goes, it disappears, and then appears. This is what we are seeing. And this type of a wave is spread all around in the universe. That is why sometimes we also behave in the similar manner. We sometimes do this, sometimes do that, sometimes forget, sometimes are very active, sometimes sleep. All that is happening because of our interaction. Second paradox, Schrodinger's cat, very famous example. I'll skip this, or maybe just read it out. A cat is placed in the seal box containing device that has 50% chance of killing the cat. What is the question? What is the wave function of the cat just before the box is opened? So if the box is open, what is the wave function? The wave function is, it can be having the probability of half being dead or half alive. When does the wave function collapse? The moment you open the box, it will be either dead or alive. So the probability of dead can be 0 and alive can be 1. That means you have measured the state, and the probability of dead goes to 0. And that is what we call collapse of the wave function. So the question is, if you observe Schrodinger's, what is his wave function during the experiment? When does it collapse? Now that's a very interesting question and a paradox, that while the experiment is on, if it is when you open before the experiment, that is what it is. When you open after the experiment, that is. When the experiment is on, what is the wave function? And when will it collapse? That's a very good question and a paradox as well. The question is, when and how does the wave function again collapse? What even collapses it? Why does it collapse also is a question. How does the collapse spread to remote locations also? So if it is dying, or if it is located already, how others know that it is live or dead? So those are questions. Third question is the Wheeler's delayed choice. A source emits a photon. The wave function passes through slit 1 and 2. If you can look at it, there are 2 slits given here on the left, and the light can cross through this. So we have 2 wave functions, psi1 and psi2, one with the solid line shown as psi2, one with the dotted line shown as psi1. Those are the wave functions. This is making interference beyond the slits. Now the observer can choose to either A, there are 2 things. A. Measure the interference pattern at the plane sigma 1, which is the middle one where the lens lies, requiring that the photon travels through both the slits. Now, if the sigma 1 is that place where if the photon has gone through both the slits, then only you will have the interference coming in here. Because for interference to take place, you need two light sources, at least two waves, requiring that they travel through both slits. This is the first one. Or B. B is the second position, sigma 2. Measure at the plane, sigma 2, which slit image it appears in, indicating that it has passed only through slit 2. Now look at it. There the location which you are having on this, you can have this by only one slit. You can see the solid lines cross and then come at the point 2 dash there. So it can come from one slit only. So these are two different interpretations. The observer waits until after the photon has passed the slit to decide which measurement to do. Whether he has to make this measurement 1 or 2 is a choice, and there will be a delay in the measurement of these two. Thus, the photon does not decide if it is a particle or a wave until after it passes the slits. What does this mean? Interference is essentially a quality of wave nature. So interference can be seen at the sigma 1 level, and those can also be seen at sigma 2 level, and that will happen when it goes from one slit but has passed through the two corners of the lens in between, dividing into two again. Then only interference will take place. So the two light waves which are going has two possible interpretations or interruptions in between. Apparently, the measurement choice determines whether the photon is a particle or a wave or no. So that's where the quantum mechanics has its own interpretations and different ways of looking at it. Let's see these three interpretations once again that we had. Heisenberg's uncertainty principle in the Copenhagen interpretation. The first one was Copenhagen interpretation, 6 people all blind. The wave particle duality, conjugate variables x, p and e and t. I don't know whether you understand this, but I'll maybe spend a few minutes. Using the uncertainty principle, x and p, x is the position, p is the momentum. These are two conjugate variables. If you are able to measure x accurately, there will be a change in the momentum, the blind man with a stick. Moment you locate the ball, the velocity changes. So the momentum changes. So the two variables cannot be simultaneously measured with the same accuracy or best accuracy. E and T are similar conjugate entities. The impossibility of simultaneous conjugate measurements is therefore inbuilt in the system itself. The Born's statistical interpretation that if you have the wave function, the probability is nothing but psi star, which is the meaning attached to the quantity, which is average behavior of the system. So if you look at the atom again, the electrons revolving around the nuclei, it is not one circle that it revolves on or one ellipse that it revolves on. There is a region around that, and within that there is a probability of finding the electron at any point of time. And therefore, at any point of time, the average behavior of the system is being interpreted by quantum mechanics. We can think of complementarity concepts, that the wholeness of the system, you look at one of the persons holding the leg part of it, the measurement apparatus, complementarity nature of the wave particle duality, a particle or a wave. So this is a leg or this. The uncertainty principle is a property of nature, not of measurement. So these are all interpretations. Heisenberg's knowledge interpretation, this identification of psi, which is the wave function, with the knowledge of an observer. Psi collapses and non-locality reflect changing knowledge of observer. Please let me explain. When you interpret your knowledge, say the person holding the trunk of the elephant, he identifies the psi and according to his observation. But then whatever is the total system of the elephant collapses, means it comes down to that trunk only, and non-locality reflect changing knowledge of observer. That means he is having an observation in a local manner, and all other effects or non-local effects are not taken into consideration. So that's the interpretation of the knowledge that he has. Heisenberg's positivities, don't ask. So that's the interpretation. Don't ask, don't tell about the meaning or the reality behind formalism. Focus exclusively on the observables and the measurements. That means if you as a human being have got an instrument and you have to measure a system or understand a system, you do your measurements at different points and make a interpretation after that. So which is also called parallelism. So at every parallel place, if you're doing this experiment and make your own observation, let it collapse to that particular wave function at every different point, but then you will come to a reality and understanding the meaning of the system that you're working with. So this seems to be confusing, and that is how I began with. I don't know whether I can explain quantum mechanics, but I'll try to. But I'm sure you'll be more confused than what you began with, especially after I finish some more slides. I'm still on quantum mechanical interpretations. There's another interpretation that you can think of one elephant with all the 6 people and then replica of the same, many world interpretation. So retain Heisenberg's uncertainty principle and the statistical interpretation from this, and you can see that similar systems will coexist. No collapse. What is this here? The wave function psi never collapses. This is a very good interpretation. That it is not the collapse which is happening. It splits into new wave functions that reflect the different possible outcomes of measurement. Please understand, when I usually compare this quantum mechanical understanding with our brain functions, and when we meet somebody, what is that we are doing? We are interacting with that individual. There is exchange of brainwave between me and him or her, and there are interactions which are happening. So am I looking at the locality aspect of it? Yes. But is that all that I can look at? No. I can still look at 10 places, but my focus at that angle, at that point of measurement is that talk. That is, so there is no collapse of the wave function of my observation, but that interpretation is that the wave function is split into so many parts or so many worlds, you can say. So that's a very good interpretation of looking at things. No observer. Our perception of wave function collapses because our consciousness, look at it, the physics comes to consciousness, has followed a particular pattern of a wave function split. So how do we perceive? That is the reason we as individuals, all of us perceive differently. We observe our way, the others observe the other way. There is also a saying or a reality, not a saying only, that anything that you have observed or measured has changed the system itself. What does it mean? If you meet a person today, and quantum mechanics says, if you meet a person, you have changed him or her, and he or she has also changed you. So next time you meet the same person, you are meeting a different person. Quantum mechanical systems, therefore, all the time change and evolve. And that is also true with us as an individual. We as cosmic space also keep changing, and that is the evolutionary cosmic forces which are all around, and all our reactions to this are therefore natural and only subject to interpretations of quantum mechanical behavioral pattern. Now, interference between the worlds. Now, if you have too many things, you look at 2 movies, 3 movies, you're confused about the stories of 3 movies. So, observation of quantum interference occurs because wave function in several worlds have not been separated because they lead to the same physical outputs or outcomes. So the observation of number of places or number of physical systems can also lead to different interpretation, and each observation also interfere to give you a new kind of an interpretation. That is happening most of our behavioral pattern as well. Our brain is also a quantum mechanical system. Now, third interpretation is, we had three interpretations. The third one is the Heisenberg's uncertainty principle, and these are not postulates because they can be derived from transactional interpretations. That means the moment there is an interaction between two wave functions, there is something which is transacted or there is something which is exchanged. If you know the whole of particle physics, when quarks combine together, the force which is, or the particle which is exchanged is called gluon. When the electromagnetic radiations interact, the thing which is exchanged is called the photon, the light is exchanged. So the whole of world can be explained in terms of transactions only. And there are quarks, 6 antiquarks, and then something which we refer to as leptons, where electron is also a lepton, muons, and then pions. So these quarks and leptons make the whole universe. So you have this transactions theory, which is interpreted also in a good manner, and that makes the quantum mechanics very interesting. They offer waves. So there is an offer wave. The initial wave function that you begin with is interpreted as retarded wave offer to form a quantum event. There is a confirmation wave, which is the response wave from a person where the interaction is taken. So we have one wave function, which is the offer wave. There is a confirmation wave, which is if that is psi, this will be psi star in the quantum mechanics formulas. And then the two are interpreted as an advanced wave function to proceed with the quantum event. So you will have an offer wave, you have the confirmation wave, then you can interpret the transaction. What has happened? This is called quantum handshake. So you can see the advanced as well as retarded waves as elephants on the top. The forward backward timing, the psi star psi standing waveform. This transfers energy, momentum, and other conserved quantities, and the event becomes real. So these interpretations play a big role in quantum mechanics, and that is why I had begun with quantum mechanics with just two problems and barriers. One is the concept itself, and the other is the notation. Notation is still easy. Interpretation is based on how free you leave your brain and imagine. Einstein used to imagine that he is flying on the light rays. So a light or a photon particle was moving with that speed, and he was catching onto that, and he was flying. And he would imagine that the Earth's, the space between the cosmos is tilted or curved. That is how he used to imagine. So imagination is more important than solving problems also. No observers. Transactions also involved. So there are transactions taking place in the cosmos where there are no observations being taking place. So they are also no different from other transactions. So observers and knowledge play no special roles. So this is not about who observed what. It is about the transactions which have taken place. And if you go back and in the system to understand what has been transacted, that is what the quantum mechanical system will help us. So it is a reversible system that we are thinking about, and they give no paradox therefore. So transactions are intrinsically non-local and all paradoxes are resolved. So this is a theory which is more general than or more general interpretation than the earlier two. So what is the summary? Is that we have three interpretations. One is the Copenhagen with the 6 concepts, the many world concept, and the advanced and retarded. There the observer knows observer knowledge to explain the wave function collapse and non-locality. What is the advice? Don't ask and don't tell about reality. Many worlds use world splitting to explain. Function collapse has problems with non-locality. Now look at it. That is the concept which is useful in quantum computing. And advanced and retarded concept, transactional concept, uses the advanced related retarded handshake to explain wave function collapse and non-locality, and it provides a way of visualizing quantum events. So that's the interpretation of quantum mechanics in 3 different ways, and we stand very strong in terms of this. The interpretation of transactional mathematically can be put as this, as the quantum matrix, where you can think if psi is a e to the power I kr minus omega t, psi star will be, you can see, e to the power I. There is a minus sign there. It will be just the transpose in terms of matrix. So this is the retarded system, that is the advanced system. And if you extend this towards in the time domain, plus time and minus time, you can see the retarded function with f1 and f2 coming into a point in the center, which are called emitters. Then advanced wave f3 and f4, they also form a cone. The one is called future cone, moving in one direction. The other is called the past cone. So the whole time domain can be understood if you understand the wave functions and the transactions which are taking place, and these are reversible in nature. In the Maxwell's equation of electromagnetism, we write it in this particular manner. That may not be of interest. I can skip this at this point of time. There's one more transactional. I would skip this part for the paucity of time. Maybe just one slide here. The role of the observer in the transactional interpretation. In the Copenhagen interpretation, which is the 6th blind observer, they have a special role as a collapser of wave function. This leads to problems, and the problems in the area of cosmic quantum cosmology, where no observers are present. So when you have observer's point of view, then there will be problem in quantum cosmology. How will you interpret the things? There is a problem. And in the transactional, which is the last one, 2 elephants facing each other, involving an observer, are the same as any other transaction. Thus, the observer-centering aspect of the Copenhagen interpretations are avoided. Coming to the testing of these interpretations, so you can see how interesting quantum mechanics is. You have to imagine even beyond what you think, and all possible thought processes also are possibilities, and therefore part and parcel of the wave functions that you can imagine. Can interpretations of quantum mechanics be tested? Definitely no. You cannot test these interpretations. Then what can be done? It is the formalism that makes the testable predictions. That means if you have the formula which is right, they will give you the results and predictions. As long as the interpretation is consistent with the formalism, it will make the same predictions. However, there is an experiment which is called Afshar Experiment, which suggests that Copenhagen and many world interpretations may be inconsistent with the quantum mechanical formalism. So the two, I will again skip the explanation, but give you the result of this experiment and conclude that if this is true, then these interpretations can be falsified. That means the first 2 were falsified because of the Afshar results, but you cannot interpret that still. I'll come to those slides, or maybe if I can go fast, I can show you there. Yeah, you can see the Afshar results. Copenhagen experiment predicts no interference, and the many world also predicts no interference, whereas the transactional, they predict interference, as does the quantum mechanical formalism. So if the Afshar tests are valid, then the first 2 interpretations will not be utilized, whereas the transactional things are utilized, and which is the reality. Going back, I have one more experiment based on the delayed choice, but if you feel, I can skip for some better things in the quantum area rather than only physics area. So I'll skip those, and that is the end of that part of it. Then you had asked me to speak something on some aspects of the quantum computing part, some aspects which I thought maybe put here, some models that we will think of it. Then what is tensor product, representing states, how do you represent them, postulates of quantum mechanics, and handling the probabilistic nature of quantum computation and the entanglement. I'm only throwing questions here or thoughts here, thought waves, which you can start taking down maybe, or listening to it may give you some ideas. Oh, this may be worth studying later or following it up later. If you look at the algorithm, what are the things that we must focus on? The execution time. Are you using an algorithm which is faster or slower? Look at it. And there are two types of time, asymptotic time and the wall clock time, of course. Then size of memory, the space that it is using. Then ease of programming that you are doing. And then there are multiple objects also. And of course, if you have multiple objectives for one particular experiment or study, you can have results everywhere, but there is no single winner. There is a principle of invariance here, that if you have interpretations of an algorithm, then should the result be different? No, the result has to be same. I'm moving faster. You can compare algorithms also to make study which algorithm is better and which is not, in terms of what is actually happening in the world now. There are very, very simple operations in quantum mechanics. When there is a state which we have defined, then there will be states which will be operated by some operators, and it will result into the measurement corresponding to that state. For example, if I'm interested in finding out what is the energy of a particular particle or electron maybe at some particular time when it is getting excited by so much of energy in a system. So what is happening is you are impacting the state, which is the initial state of the system, by that operator, which is called the energy. Now, the moment you give that energy into that system, there is an operation which is taking place. That operation will give you a result. And that result is the result of the measurement that you have done on the system. So these operations work in quantum mechanics, and there are conditions that we apply on these operators, that they cannot be unreal. They have to be giving results in the real time, as well as in the complex world that we have so far known. It cannot be only imaginary or too large or too small a quantity. So a computational model is determined by what? By data interpretation and storage mechanism. And these are available in the operations that we do. You can get on to the measurement of the efficiency and the complexity. These are issues that you have in the computations, complexity. Then we are using our intelligence, or maybe I would say brain power, to reduce the problem into a simpler problem. I'll tell you an example which I did, or we did while doing my research work, that we were working in a coordinate space, XY space, but then the problem was so large, or the equation was so large, that it was spreading into 6 pages, integral equation. Now, we then transformed those equations to a momentum space. So from X space, we went on to momentum space. We did another transform there called Hankel space. So using mathematics and mathematical skills, what we do is we transform the problem from one space to another space. So what is looking as logarithmic or exponential in one space may look as plus minus in the other space. So you solve the problem in the other space and come back in the reversible manner and get your solution. That is the intelligence that physics people have been using for long. So you can again reduce either a problem to some other problem called y. So your problem x went on to another space, transformed it, and the problem became a y problem, which is a plus minus problem. So complexity also reduces, the time also reduces. You can do it with ease, with less of error in there. You can simulate these using C programs. I said what are the essential 4 things. There we have the Turing machine coming in. I have written simulating computational models. Please do this if you are interested. Write a C program that simulates a Turing machine. Write a C interpreter as a program for a Turing machine. And the computational models will be all equivalent no matter what model you use. Then modern the modern church Turing thesis, what it says, please understand that how would you prove or disprove this is an open question still available. Yes. This was another open question that we had. There were 2 open questions that I had posed. One was whether the quantum computers can be really made. There are 3-4 models that we discussed. And the other was whether the quantum computer can really solve the NP-complete problem. Let us understand what is an NP-complete problem. What is P? P is that class of problems whose solutions can be found in polynomial time. Polynomial time gives P. So problems whose solutions can be found in polynomial time is P. What is NP? Is the class of problem whose solutions can be verified in polynomial time. It is not solutions found, it is verification. The third is the NP-complete problems, those which every other problem in NP reduces in polynomial time. So what is NP-complete? Are the problems those to which, these are NP-complete means these are the problems to which every other NP problem reduces. That means if you have an NP problem which you are ready to verify in polynomial time, right? This will reduce to that NP-complete problem. Now, the open question again is whether NP is same as P. Not really. So there are intricacies here, but maybe if quantum computer comes, the 2 may look similar because polynomial time concept will go away there. So what are other orphan problems which are unattended or unclaimed so far, that those in NP or P but not NP complete, assuming this, these are problems existing. Number factoring is still a big game, and you can play with this using quantum computers in a much better manner. Graph and automorphism are those open questions again. So how could you disprove this church Turing thesis? This is something that is again an open problem. So you have to define a computational model to understand and solve these issues. But ultimately, you can see you can back to quantum mechanics again. So you're back to quantum mechanics. Having said and tried to make what are the types of problems and open problems, if you don't understand quantum mechanics, you will not be able to use its power. So there are 4 postulates which are again important. The state space itself. Now we, as quantum mechanical person, work in the Hilbert space, which is infinite dimension. But then quantum mechanical systems or the computational systems would only need finite dimension. So this is one thing, that you will have to work with the finite dimensional Hilbert space. So state space is defined. It is not infinite dimensional as in quantum mechanics. Postulate 2. You will have to have unitary matrices or operators defined, found, discovered to really understand the evolutions of systems. It can be in terms of matrices, and all its mathematical operations are looking like juggleries and difficult, but they are not. They are practice dependent. The third is the measurement itself. The 2 forms that we understand in quantum mechanics are the Hermitian observables and orthonormal. So if you understand a system in one basis and transform the same system in another basis, like you can see, if I think of a vector, a vector can be put as x and y. So x and y are the basis in terms of which a vector can be defined. But a vector can also be defined in terms of r and theta. So where instead of x-axis, we say r cos theta, and the other one is r sin theta. So these are two different bases in which the same quantum mechanical system can be observed or put, but there are I would say problems where you will prefer to work in XY system. There are problems where you would work in R theta system, especially where there is a spherical symmetry that we are thinking about. The extent is too large, and the phenomena are spread out evenly. And if it is not spread out evenly, then in terms of R theta, it may not be possible, and so on. So quantum measurements are decomposed in terms of one or the other basis systems, and then you observe and then interpret. Fourth postulate is the composite system. Ultimate study is of a composite system. All these days we have possibly mastered hydrogen system, helium system, maybe carbon system. Not composite systems have still been understood, because here a new type of a thing comes in, where if I have an infinite dimensional or even finite dimensional waves state space and another wave space, and when they interact and make a system which is composite, it is very, very difficult to solve those issues, and we have to adopt to or go to the realm of the tensor products, and most of the systems being really complex, we tend to get confused into that system. Therefore, especially in the classical computation so far, the moment we get onto the quantum computational system, studying about composite systems will be much better. So going back to quantum mechanics, therefore, is the only option that we have. This is what I just said: Hilbert space and the tensor product. If you still want me to continue, I'll continue on other aspects of quantum mechanics. But most of it was already covered here and there. Therefore, I thought to put it at the back in case time permits, or somebody has a question, I can. I think it is, what is the time like? Oh, it's 3:50. I have 10 minutes. Shall I continue?
Yes, sir. You can continue, sir.
Okay. If I continue, then I skipped that part because those were already covered by so many speakers. Understanding by some exercise. Just a few exercise, 10 exercise points here. And I will be reading. Please listen to me, and I'll share the slides. Exercise 1. What is computation? In a very, very informal manner, computation is nothing but a calculation done by a physical device or a computer. In an automated manner. You are not doing it, they do it. The main idea is, instead of doing calculation on our own, we can use some physical device to do it. So what is a physical device? It's a computer. Is it able to compute because of the laws of nature? In other words, because of the properties of current and voltage, we can implement the gate concepts that we have been using, and or NOT gates, which provide basic building blocks. And that's the classical computer architecture. The fundamental idea or any physical law or a process can potentially be used to do computation, led to the origin of quantum computation. I'm sure now you can understand this. When computation is done, I'm only explaining the problem. I'm sure some aspect of answer is here. What is quantum computing then? When computation is done using the principle of quantum mechanics, it is called quantum computing. That's all. In other words, if it is done on a physical device obeying quantum mechanical laws, then that's quantum computing. There are limits and models that we have already talked about. Exercise 3, everything in the world obeys quantum mechanics. Everything in the world obeys quantum mechanics. Classical mechanical systems are part of quantum mechanics in a particular domain where mass is large, velocity is low. Okay, and quantum mechanics, when mass is low, velocity is high. So we know that classical and quantum laws behave similarly in a large scale system. It is only very small system that quantum mechanical peculiarities come in. So it is understood that quantum computers are useful only when these peculiarities can be exploited to do these computations. I'm sure you understand this. Why do we need this quantum computing? We have been highlighting these issues and problems. The Church-Turing hypothesis has to be proved, and we must see that we are not violating any of the physics laws. Is it possible that some weird physical law might compute things much faster than the classical Turing machine? Since we believe that quantum mechanics is the theory of everything around us, it makes sense to have a quantum Turing machine also instead of a classical one. And there are attempts already made on this. Why do we believe, exercise 4, why do we believe that the quantum computers can be faster than the normal classical computers? I think I have already spoken about it, but if you want, I can read it out. Quantum mechanics has strange properties of superposition and entanglement. So superposition basically says that quantum systems can not only have classical states, but it can also exist in a mixed state, which is the superposition. Naturally, the number of states are infinite, and we can have this. Next also is that it has the property of entanglement. If you understand entanglement well, and then you understand that we have made a measurement on one part of it, the other part is already done, which means it is fastest. So we are ready to answer some of the questions which we initially put. The basics required to understanding quantum mechanics we have done. Linear algebra, we did little bit of it. I have left the rest real tasks. Introducing the models, we said there are two, the circuit model and the adiabatic model. Then postulates of quantum mechanics, we discussed 4 postulates, and some algorithms we can end with, also talk about the error correction and so on. One algorithm here is Deutsch algorithm. I don't think I should get into this because that's the area the computer scientists should get in. What are the other bases for the state of quantum bit? Well, linearity and non-linearity are the concepts in the mathematical realms. And if you think of a 2 by 2 matrix, or then you can also think of 2n by 2n matrix, and therefore largest possible matrix can be the basis which will take care of the biggest and biggest type of problems and data sets which can be solved using quantum computers easily. So it's an infinite possibility. Exercise 8, check that this gate is unitary and write the matrix representation. See, evolution of a system and unitarity was discussed earlier, and if you understand the whole of quantum mechanics, the concept about why unitary, why normalization, why orthogonal, all that will make sense, because we have to make real physical observation. So that's how there are boundaries also put around quantum mechanics. Exercise 9, what will happen if we need the state this as the data qubit or this? I think you may forget about this at this stage. Otherwise, one can simply answer the last sentence here. These measurements will not allow us to compute F0 or 1 F together, and therefore there is an uncertainty, and therefore while you are measuring, you will always fall back to either 0 or 1. You cannot have simultaneously 0 and 1. There is a need for speed up. Classical digital computers have their limitation speed, whereas they have very high speed. These are all talked again earlier. Quantum computing powers, problems open still, integer factorization, quantum database search that we had talked about, Shor algorithm and the algorithm by Grover. Then practical quantum applications are the quantum mechanical simulations in physics, chemistry, material science, nanotechnology, etc., and crypto analysis. See, crypto world is altogether a new world, not a new world I would say, but it is a world which is so badly required in the times to come. We have cryptocurrency already inside, so the quantum system can be 100% secured and using this cryptography, and this is because the quantum key distribution is fastest possible, as fast as speed of light, and the moment somebody makes a measurement in between, this system changes. Therefore, nobody can really trace back what was being sent or being looked at. So it's a totally secure system that we are thinking in terms of quantum computing. Going back to the history, it may not be right at this stage. Yes, this I can maybe spend the last few minutes. What are the other candidates for quantum computers? You can see we had discussed 3-4 earlier. We have a possibility of superconductor-based quantum computers. I just said my own theory was in the 3 realms. One was astrophysical plasma, the solar plasma. Second was the subnuclear particles, quark-gluon plasma. And the third was the superconductors, the Cooper pairs, and then same theory being applied there. So if the quantum computers can be made in terms of the superconductor or superconducting pairs or particles, you will have solved the problem of energy also forever, because these superconductors have no resistance at all. So no resistance means no power loss. No power loss. And if you're using the magnetic systems, then magnets on their own will make the system move without loss of energy. That's how we are in the superconductor world, in case we can. Ion trap we discussed. Nuclear magnetic resonance I said. Then there's a new thing, quantum dot on the surface. This is based on the quantum dots, nanotechnology based quantum computers. Lasers acting on the floating ions, these are same as ion trap. Cavity quantum electrodynamics I skipped, but then that's also one possibility. Then molecular magnet based quantum computers is another possibility. Then ESR quantum computers, another very, very important candidate. NMR I have already said. So there are many, many ways of doing it. We have still not crossed any substantial mark to claim that we have made quantum computers. So what are the problems? Quantum computing problems, the current technology, 40 qubit operating machines needed to rival current classical equivalents. Just 40. And I think we have crossed 54 or so. At least on claim basis by IBM, some by Google, and so on. What are the problems and the errors that we generally see in the quantum computing is the decoherence, because the moment you measure the tendency of a quantum computer to decay from a given state into incoherent state as it interacts with the environment is a source of error. But there are issues and that we can make these corrections of the error also. So error rates are typically proportional to the ratio of operating time to the decoherence time. And that's the present problem, again, open for research. I think that is where I can stop. If it is still 4, I would have my best wishes for all of you doing quantum computing in future. Thank you.
Yes, participant, having any queries?
Sir, does asymptotic algorithmic analysis are also holds for quantum computing?
Yes. There is a possibility. But I would not know the details, but then that is also a possibility.
No, I had this query because of 2 things. One is there is a possibility of one state among the group of states, as we have number of bits, not only the 0 and 1, we have number of qubits in fact. Second is the overall discussion is the exponentiality is a speed factor. So I have just a doubt over this. Thank you, sir.
Yeah, as you said, I have not worked in that area. There is a possibility is what I can say. I did mention, and there was a word used somewhere in this slide. It was there in, but then details can be.
Sir,
Yeah.
one query put in a chat box. Can I read, sir?
Yeah, please.
From the Ramakrishna Reddy. Then questioning any relation between quantum computing and quantum dot cellular automata.
Again, not my field, but I only again mentioned that quantum dots are the
Cellular.
candidates. Pardon?
Quantum dot cellular.
Yeah. Quantum dots are the candidates which are also in the line for building the quantum computers. But details, I have not had the time, or maybe that area is not at all mine. So I have not ventured into it. I will not be able to answer details.
Yes, any query? Okay, then we will conclude. Then I request to Dr. S.V. Gumaste sir, HOD of IT department, to give the vote of thanks. Over to you, sir.
Yes, sir. Thank you. On behalf of MIT's Institute of Engineering, I am thankful to you, sir, for enlightening us by sharing the information on quantum computing. This session includes how quantum computing concept relates with the quantum detailed physics and the explanation over the basic terms like discreteness, duality, and uncertainty. Quoting and explaining the real-time example is the beauty of today's session. A very nice session, sir. Thank you very much. We are really proud to have you in this session, sir. Thank you, sir.
Thank you. Thank you. Can I take leave now?
Yes, sir. Yeah. Thank you, sir.
Thank you. Thank you.
Yes, all of you fill the today's attendance, last session attendance, and feedback form. Thank you.
Participants, if you're facing some problems, then please wait for 10 minutes. Team is working on that link, and it will be the problem will be resolved in 10 minutes. So please wait. This is regarding feedback form.
Now it is working, sir. Now it is working, sir.
Yes, it's working. Now you can submit your feedback. Thank you.
Thank you.
Yes.
Thank you, sir.
Now welcome. Mehdi ma'am, form is updated now. Please check.